Thanks a lot. Thanks a lot for the invitation, and thanks a lot for the nice introduction. It's a pleasure to be traveling through my computer, and being in Australia is very exciting. And it's a pleasure to tell you about this project, which is in fact a series of 2 papers. So one of them was posted on the archive in October, I think, and one of them will be posted on the archive anytime soon. And these 2 papers are in collaboration with Daniel Kious, who is also at Bath, and Bruno Schapira, who is based at the University of Marseille. And this project is about ants finding shortest paths using reinforcement learning. And we got inspired by a book which is called Ant Colony Optimization. So this is a book of biology and math and also computer science, where the authors Dorigo and Stutzler show how we can design efficient reinforcement learning algorithms that are inspired by the real behavior of foraging ants. And so they also cite biology paper with experiments on ants and all that. And in this book, there is one algorithm which is how to find shortest path in a graph, and this is and we wanted to design a probabilistic model for this problem and show that in this probabilistic model, indeed, the ants find the shortest path. So that's the idea of the talk. And I have to mention that there are also lots of papers in math biology where people have mean field models for this. So they have a graph and they have some flow of ants and they solve some PDEs, and they show that the flow indeed concentrates on the shortest path. But what we wanted to do is really have a probabilistic model for that. So in our model, we fix a graph. So the graph G is fixed throughout. It's a finite graph. And that's all for now. So it's a graph G with set of vertices V and sets of edges E. And in this graph, we have marked 2 nodes, node N, which is the nest of the ants, and node F, which is the source of food. And so the idea is that the ants are going to perform some random walks on the graph, but eventually what we want to find, what we want the algorithm to output, is the shortest path between the nest and the source of food. And when I talk about distances in this talk, I always talk about graph distance. So each edge has length 1, right? Great, so I'm going to describe to you the algorithm. So the algorithm is going to be described in terms of edge weights. And the edge weights are going to represent the pheromones that the ants leave behind them. So at time 0, all edges have weight 1, right? So this is just to start. And each ant, so at time N, I'm going to send 1 ant to explore the graph, right? And each ant performs a random walk from N, so from the nest, and it stopped when it first hits the food, to F, from N to F. And with transition probability proportional to the weights. So let me tell you on a little example, let me tell you what that means, just so that we agree, but it's really the standard thing. So let's have a look at this little drawing here, and let's imagine that the weights of these edges are 1, 3, and 2. And let's imagine that the ant is sitting here, and it needs to decide what's the next step, right? Where is it going to go next? And so it's going to cross this edge with probability proportional to 1, this edge with probability proportional to 3, and this edge with probability proportional to 2. So in the end, it's going to go here with probability 1/6, it's going to go here with probability 1/2, and it's going to go here with probability 1/3. Right, so it does that so this describes the transition probabilities of the random walk performed by each ant. And now I need to tell you, how do I modify the weights, right? So what I do is that each ant does a walk from N to F. And once it's reached F, I'm going to update the weights before the next ant starts. Okay, so then after the ant reaches the source of food, we update the weights. And how do we do that? We just do by doing +1. So we do +1 to, and here I'm going to be a bit vague, a subset, but I'm going to be more precise later, a subset of the trace of the ant. So the trace is all the edges that have been crossed at least once by this ant, and we're going to do +1 to a subset of this trace. Okay, and you can imagine that this really represents the ant leaving pheromones behind itself, right, when it walks. Before telling you how we do that, I just want to insist on one thing on this slide. It's on the fact that this is really a reinforcement model, right? Because we reinforce the edges by doing +1 on them. And I want to say it's a linear reinforcement model, because you see 3 here represents somehow the amount of pheromones that have been left on this edge, and the ant crosses this edge with probability proportional to this number. So this is linear reinforcement as opposed to sublinear or superlinear reinforcement, which also exists in the literature. But in this case, it's linear reinforcement. So the ants react linearly to the weights. Great, so now let me tell you which subset of the trace is reinforced. And there are 3 different cases which somehow define 3 different models. And I'm going to tell you results about these 3 slightly different models. The first one is maybe the most natural one, which is do +1 to all edges in the trace. Right, so basically the ant just leaves pheromone on all edges that it has crossed. So I'm going to give you an example here. Let's imagine that the ant here went through, let's say it explored the graph doing this complicated trajectory, and eventually it reached F. In this first model, which I call the trace reinforced model, I'm going to do +1 to all the edges that belong to the trace, which are all these edges here that I put in bold and orange. So basically all the edges except this one, because this one hasn't been crossed by the ant. So this is how, in this first model, the trace reinforced model, this is how I update the weights. In the loop erased case and the geodesic case, which are the 2 other models I'm going to define now, the idea is a bit different. So if you want here, we can imagine that the ant leaves the pheromones on the way forward to the source of food, right? And then it stays at the source of food and, you know, eats happily, and the other ants then try to do their walks from the nest to the food. In the loop erased and geodesic, the idea is a bit different. The idea is that the ant reaches the food, but it doesn't leave pheromones on the way forward to the food. Then once it's at the food, it gets really excited because it's found some food, and it starts leaving pheromones, but on its way backwards to the nest. And in fact, I mean, this sounds a bit crazy, but apparently biologists have considered this kind of model. And in fact, they have considered the loop erased model that I'm going to tell you about. So in the loop erased model, the idea is that the ant is going to go back to the nest, following its trajectory backwards in time. So it's going to follow the trajectory, the red trajectory backwards in time, but it's going to erase loops. So if you don't know what erasing loops mean, it doesn't matter. I'm going to give you an equivalent definition now. So the idea is that the ant is going to follow its trajectory backwards. So I'm going to do that now in green. So I go back this way. But when I have the choice between 3 edges that I crossed on the way forward, I'm going to choose the one that I crossed the earliest on the way forward. So here on the way forward, I first came to that node, to that vertex, through this edge. Therefore, this is where I go now when I do my way backwards. Then here I have no choice. I came from the left. And here again, I have a choice between this edge and this edge. But the first time I arrived this way. So I go back this way here. And I do +1 to all the edges in green, right? So yeah, so I just go back doing a loop erase version of my forward trajectory. Great. In the last model, which as far as I know hasn't been considered in the biology literature, but is quite natural if you're a mathematician, is the geodesic model. So again, I'm going to take exactly the same example. So let's say the ant has done this trajectory. I chose an example for which the three models are different, right? But let's say I do this trajectory, and this time, so you have to imagine that the ant, it's a bit like you when you're hiking, right? So you hiked at random, you found a source of food or a nice lake in the mountains, and you want to go back, and you have in your head, you have a partial map of the graph somehow. So you have a partial map, so you don't know all the paths, you don't know all the roads, but in your partial map, there are some shorter paths for you to go back from the food to the nest, and you choose to go through one of the shortest paths, right? Because you're a bit lazy, or at least I am. So here I have the partial map is all the edges that I've crossed. So all the edges except this one, I don't know about this edge. And I want to go through one of the shortest paths. And I'm saying one of the shortest paths because here, in fact, I have two. I have the green path here, which is of length 3. So I have explored this path and it's of length 3. But there is also another one. And I chose this example because there were two, and I can tell you about what happens when there is a tie. So I also have explored this path. And so I'm going to go back through one of these two shortest paths in my partial map of the graph. And I'm going to choose one of these with probability 1/2. So when there is a tie, I just choose one of the possible options with probability 1/2. And here with probability 1/2. So either I do +1 to all the purple edges, or I do +1 to all the green edges. Right. I hope the models are clear. So these are the three variants of the model we're going to study. And they only differ by the reinforcement rule. That is just a bit different, right? So which edges do I reinforce? So before doing anything else, I want to tell you about the results, but also the conjectures we have. So arguably there are more conjectures than results, but at least it proves conjectures. At least it proves that the model is rich mathematically, which is great. So let me introduce a notation. I'm going to denote by WE of n, the weight of edge E at time n. Just to fix ideas, the weight at time 0 was 1 by definition. And so at time n means after the nth ant has performed its walk and I've updated the weights, right? So to state our results and conjectures, it's useful to define some vocabulary. So there are two sentences or two phrases I want to define. So we're going to say that the ant's process converges if there exists some sequence chi-e indexed by the edges of my graph. These can be random variables, right? Such that almost surely the weight of the edge E, when I divide it by n, so I renormalize it by n, then it converges almost, I've already said almost surely, then it converges when n goes to infinity to chi-e. So it's just saying my renormalized weights converge to some values which can be random, but there are no oscillations, right? So I have some conversions. And this is true for all E in my set of edges. The second sentence is what we are interested in. So we say that the ants find the shortest path if, almost surely, if in addition, in fact, sorry, so we need if the process converges, and in addition, almost surely, the only edges that have a non-zero weight are the edges that lie on a geodesic, so a shortest path between the nest and the source of fluid. So E is on a geodesic. Geodesic just means shortest path between N and the source of fluid. So it means that edges that don't lie on the shortest path between N and F have a weight that a renormalized weight that converges to zero, which means that asymptotically, when the number of ants goes to infinity, almost a proportion zero of the ants are going to cross that edge, right? So this means that we find the shortest path, right? The algorithm outputs the shortest path as being the set of edges that have a renormalized weight that doesn't converge to zero. Great. So these are the definitions. Now, what are the results? I'm going to give you our first theorem, which was in the first paper, which is on the archive. And our first theorem is about the model LE, so the loop erased model. And it only holds if G is a series parallel graph. And I'm going to define this just after I stated the theorem. So let's be just a bit patient. Series parallel graph, maybe you know it already though. Then the ants find shortest path. The shortest path. Great. So what's a series parallel graph? So I'm going to give you a recursive definition, but you're going to see that these graphs are very natural for our model. So I think they originate in electricity, and it's a family of graphs where two nodes are marked. One of them is called the source, because this is where the electricity comes in, and the other one is called the sink. This is where the electricity goes away. So it's very natural for us to see the source as the nest and the sink as the source of fluid. And in the probability literature, you can also find them in a series of papers by Ben Humbley and co-authors, and they look at different questions on some random models of series parallel graphs, and they call them hierarchical lattices. So let me give you a recursive definition. So a graph G is a series parallel graph if, so the base case is that, so the simplest of series parallel graph is just two nodes with one edge between them. So the top node is the nest, the bottom node is the fluid, and I just have one edge between them. So if G, this is G. The second case is that G is two series parallel graphs that have merged in series. So here, I just put one series parallel graph on the top, and I merge the source of fluid of this top graph with the nest of the bottom graph, right? So this is a graph G1, this is a graph G2, and G1 and G2 are smaller series parallel graphs that I merge in series. And the third case is that I merge two series parallel graphs in parallel, right? So I merge their two nests into one nest, and I merge their two sources of fluid into one source of fluid. So again, here on the left is just means any series parallel graph, and on the right, any series parallel graph. So this is G1 and this is G2, and I merge them. So this is a recursive definition, but this is how you define series parallel graph. Okay, so this theorem is only for the loop erased model, but we believe it would also work for the geodesic model, but we haven't written the proof because we believe the proof is more complicated. Of course, as you can imagine, the proof is done by induction here, right? Because we have a recursive definition, therefore it's convenient to do the proof by induction, right? So we assume the proof holds on G1 and G2, and we want to prove that it holds on G, and similarly in that case here. Great. So once we had proved this model, this theorem, we thought, okay, great, we're going to prove the theorem for all graphs, but let's start with the simplest graph we can think of, which is not series parallel. And this graph is the one I have pre-drawn here, which I call the Lozange graph, because it looks like a losange. So it's a losange with an extra bridge here in the middle. So this is not series parallel, and it's really, I mean, it's the simplest we could really think of. And for this graph, we managed to prove a second theorem, which says that for this time for model G, although again, we believe it would also be true for the loop erased model, but we didn't prove it because we also believe it would be harder to prove for the loop erased model in this case. But for model G, so the geodesic model, on the losange, so the losange is just this graph that's drawn here, the 5-edge graph, then the ants find the shortest path. And in fact, I'm just going to tell you what we prove really, because it's a bit more precise than this. So I've numbered the edges 1, 2, 3, 4, and 5 here. So this is just an arbitrary numbering to be able to state theorem. So we're able to prove that the weight of edge 3 renormalized by n converges to 0 almost surely when n goes to infinity. And all the other limits, so the chi I, so for all I not equal to 3, chi I is also non-zero almost surely. So I have a non-zero weight on edges 1 and 2 and a non-zero weight on edges 4 and 5. So we do find shortest path for that model on this graph. So here you could be a bit disappointed in me and Daniel and Bruno being like, come on, in your first theorem, you treat all the series parallel graph is like many graphs, right? Infinitely many graphs in one theorem. And in theorem 2, you just look at this very simple 5-edge graph, right? You should be a bit more ambitious. But in fact, surprisingly, you can go and have a look in our paper. The proof of theorem 2 is much longer and harder than the proof of theorem 1, which makes us a bit pessimistic about whether we could generalize our results to any graph. But in fact, we still conjecture that, so let me tell you about our conjecture. We conjecture that in models LE, so loop erased, and G, ants always find the shortest path. But we're not able to prove it. And as you can see in our results and conjectures, I started telling you about models LE and G, because in fact, even though maybe they are a bit less natural to define as the trace reinforced one, they are easier to study, right? And the trace reinforcement one is harder to study. And in fact, it's the object of our second paper, because we only were able to find results after the first paper because it was harder. So let me tell you what happens in model T, so the trace reinforced one, which is the most natural one, right? I do +1 to all edges in the trace of the ant. And let's start with the good news. So the third theorem says that in model T, if the graph is tree-like, and I'm going to tell you what this means very soon, and if the distance between N and F is 1. So I just have, my ants can go from the nest to the food in one step, right? I just have one edge between N and F. So if the distance between N and F is 1, the graph distance, then the ants find the shortest path. So I've just drawn here for you below a little tree to explain to you what is a tree-like graph. So a tree-like graph is just a tree rooted at the nest. So I've drawn here a tree, and then the source of food is just the node obtained by merging all the leaves of the tree. So you imagine we just merge all the leaves of the tree into one node. So I'm going to draw this like this. So here I'm not adding edges between them, I'm really merging them into one node, and this node is then the source of food. And here I've really drawn a tree which really falls into the framework of theorem 3, because there is one edge between N and F, which means that the distance between N and F is indeed 1. And so on this graph, the urns would find the shortest path in model T. And just to tell you, a tree-like graph is also series parallel, right? So it's a subclass of series parallel graphs. Now to the bad news. So the bad news is that in fact, in general, urns don't find the shortest path. And I'm going to give you some counter examples to that. So in model T, on the following graphs, the urns process converges to some limiting weights, and I'm going to write these limiting weights here in green, KE, where, so I've put it in green because I'm going to now draw, so the graphs are pre-drawn, but I'm going to tell you in green, I'm going to write the limiting weights of the edges. Okay. So the first graph we looked at is this graph here. Why did we look at this? Is because we thought, okay, in theorem 3, the assumptions on G were that the tree was tree-like and that the distance between N and F was equal to 1. And the question we ask ourselves is what happens if we remove just this assumption, but we keep the fact that the graph is tree-like. So one example of that is this very simple graph where I put P edges on the left path and Q edges on the right path, and I'm asking that P and Q are more than 2 because I don't want to have this assumption here. So the distance between N and F is larger than 2, and I just have 2 paths like this. And the question is, if P, say, is less than Q, do the weights of all these edges on the left here go to 0? And unfortunately, the answer is no. But in fact, we can say more. I can tell you what the limiting weights are. And the limiting weights are of the form alpha squared, alpha to the third, etc. on the left branch until alpha to the p, and beta squared, etc., beta to the q on the right, where alpha beta is the solution on 0, 1, but open, which is important because it means that neither alpha nor beta is equal to 0, of alpha to the p plus beta to the q equals 1. So I don't find shortest path on that example, which is a bit disappointing. In the second graph we looked at, so this time we thought, okay, so if I keep this assumption, but I remove this one, I don't find shortest path in general. What if I do the opposite? So I'm not tree-like, but the distance between N and F is 1. And we thought, let's have a look at series parallel graphs. And so this graph here, which we called the cone, is series parallel, and the distance between N and F is 1. So we thought, okay, well, let's have a look. And it starts quite well. So the weight of the edge on the left is indeed going to be 1. So a proportion 1 of the urns are going to go to the source of food going through that edge. And in fact, you know, this is a consequence. As a consequence of that, the weight of this edge here is 0. So none of the urns, asymptotically, almost none of the urns go through that path. But bad news, the weights of these two edges in parallel is 1/3, which means that the urns although almost all of them are going to go through that edge eventually, lots of them are also going to waste some time just going through that edge, these edges here. And therefore, we don't find shortest path. Okay, so bad news. And finally, we thought, okay, let's have a look at this losange. So here there is no good reason. We just thought it's because we looked at it in the first paper. So let's have a look what happens in this model T, right? And here again, it's quite interesting. We managed to prove that we converge to 1/2, 1/2, 1/2. So here again, sorry, 1/2. So here again, bad news because this weight doesn't go to 0. So we don't find shortest paths. And what's maybe a bit funny is that we managed to prove that these two edges have a weight which I call W star, where W star is the unique solution of, and I'm just giving you this equation just to show you we have it explicitly, although it's not very informative, but it's 2W3 plus 4W2 minus 2W minus 3/2 equals 0. So we can characterize these weights. And what's interesting in all these examples is that we have convergence of the process, of the urn process, to limiting weights chi-e's, which I wrote in green, but also, surprisingly maybe, these weights are all deterministic. And there is no reason for that, right? So there is a conjecture, which is that, in fact, for all graphs, the limit should be deterministic, except if we have double edges that are linked to the fluid. But otherwise, we believe that on any graph, the weights should be deterministic. The limiting weights, the chi-e's, should be deterministic. That's it for the results and conjectures. And now I'd like, before giving you ideas of the proof, I want to give you a very quick literature review on urns in the probability literature. So it's very quick, and I pre-prepared it. So other papers on urns. So maybe you've seen the recent paper of Erhard, Franco, and Reitz, which is called the urns mill. And so it's also about urns, but it's a bit different because there is one urn and the reinforcement is not linear, it's superlinear. And it's quite similar, I think, at least just from reading, if you just read the abstracts, it's quite similar to a paper of Le Goff and Raymond from 2018, where also there is one urn and the reinforcement is superlinear. And in these cases, somehow there is one urn which self-reinforces itself somehow with superlinear reinforcement. And what happens is that eventually the urn just ends up going through a cycle forever. And that's why it's called the urn mill, this paper, because they end up circling like this forever. Aside from these two papers, which are on urn, there are other papers about more general reinforcement that are related to our project. And these are about interacting, so Pólya urns with graph-based interactions. And so there is a paper from 2015 from Benaim, Benyamini, Chen, and Lima, in which they look at this. So here it's a bit similar, except they look at superlinear reinforcement, but also sublinear and linear reinforcement. But the difference is that instead of reinforcing a whole path of edges, they reinforce only one edge at each time. So it's a bit of a different model, but really it's related, I would say. And then there are also a series of papers about worms, which are basically a generalization of this model of Benaim, Benyamini, Chen, and Lima. And I think that the first of these papers is from 2016 by van der Hoofdstad, Holmes, Kuznetsov, and Russell. Okay, so this is a very quick literature review. Let me tell you about the methods of proofs. We use basically three tools. We use Pólya urns, which shouldn't be surprising if you know my other papers and my PhD thesis. We use electric conductances. So this is just a method to calculate probabilities for random walks on a weighted random graphs. You can go, for example, and look at the book of Lola and Limich, where this is very well explained, but it's a very convenient tool for us. And lastly, and maybe most importantly, we use stochastic approximation methods, as in the book of Michel Benaim or in the survey of Pimentel. And in particular, for model T, we almost exclusively use the ODE method, which is a method for analyzing stochastic approximation. So the methods of proof are a bit different in the two papers. So for model G and LE, so geodesic and Looperate, we use really a mixture of these three methods. And in model T, we almost exclusively use the ODE method for stochastic approximation. I would like to go through two very simple examples of graphs. And these two very simple examples are going to hopefully make it clear for you why these three methods are going to be useful for this problem. So the first very simple example is going to sound a bit silly because I'm just going to take so my nodes N and F. So this is N and this is F. And I'm just going to put two edges between them. Okay, so here there is really no shortest path to find, but let's have a look at how the model behaves on this graph. And in fact, if you think about it a little bit, you're going to realize that the three models are all equivalent. So sorry, L, E, G, and T are all equivalent on this graph, because the only thing you can do is either do, so the ant either goes through the left or it goes through the right. And in all models, it means you either do +1 to the left or +1 to the right. For convenience, let me just call these edges edge 1 and edge 2, right? Just to be able to write things. And the first calculation we have to make, somehow to understand the model, is the following. We ask, what's the probability that the ant is going to reinforce edge number 1? So what's the probability that I do +1 to the weight of edge number 1, knowing all the weights at time n? Right. So here it's very easy. It's equal to the probability that the ant chooses to go through edge number 1. And we know that the ant chooses which edge to cross with probability proportional to the weights. So this has to be W1 of n divided by W1 of n, divided by the total weight, right? So W1 of n plus W2 of n. And here, if you know about Pólya urns, you've already recognized a Pólya urn. So if you don't know about it, let me tell you what I see immediately when I see this formula. I see an urn with purple balls and green balls in it. And I see that W1 of n as the number of purple balls in my urn, and I see W2 of n as the number of green balls in my urn. And this formula tells me that I pick a ball uniformly at random in my urn, and with this probability, it's going to be a purple ball, right? And in that case, what do? I just add one other purple ball to the urn. So it's the standard Pólya urn where you pick a ball at random and you put it back in the urn together with another ball of the same color. And you do that, so on and so forth. And it's an exercise we give to undergraduate students, right? So it's just a little martingale, it's very nice. And you can do calculations explicitly. And you can show that in that case, the proportion of purple balls converges almost surely when n goes to infinity to a uniform random variable on 0, 1. So the renormalized weight of the first edge goes to a uniform u, and the weight of the second edge goes to 1 minus u. So here my chi-e's, my limits are random, and a positive proportion of the ants go through the left, a positive proportion of the ants go to the right. Okay, great. So let's make things a bit more exciting by looking at a graph in which I actually have one path that is shorter and that I want to find. And this is going to be this little graph. So I'm not being very ambitious here. I'm just looking at a 3-edge graph. Edge number 1 is going to be on the left here, and I'm going to call edge number 2 and 3 the 2 edges on the right. And here again, if we think about it, model LE and model G are equal on this graph, but they are not equal to model T. So in these two models, I can only do either +1 to this edge or +1 to these two edges. But in model T, I could do, for example, +1 to these two edges. And this is not allowed in model LE and G. So let's have a look first at model LE and G. And again, so the calculation starts similarly. I'm looking at what's the probability that I reinforce edge number 1 at time n, knowing all the weights up to time n. And so this time it's a bit complicated. It's basically the probability that the unt eventually goes through this edge and not through that edge when reaching F. To calculate that, this is when we use electric conductances. So let me do a little drawing. I'm going to open my graph by dividing F into two nodes, which I'm going to call F1 and F2. F1 is going to be the one that is linked to edge 1. So my source of food and my nest, sorry, is here. And F2 is going to be the one that is at the end of the long path, 2 and 3. And so the probability that I reinforce edge number 1 is the probability that starting from n, my random walk on this graph is going to reach F1 before reaching F2. And what the electric conductances method tells us is that this is equal to the conductance, the effective conductance between n and F1 divided by the effective conductance between n and F1 and the effective conductance between n and F2. What are these, right? So the effective conductance between n and F1, since there is only one edge, it's just the weight of this edge. So this is just W1 of n. And the electric conductance between n and F2, well, here you just apply the formulas you learned at school, or at least I learned them at school, of how do you calculate the conductance of two things, two resistances in series. And the formula here is a bit complicated. It's just 1 over the conductance of the first edge, which is just the weight of this edge, plus 1 over the conductance of the second edge. Okay, just a little nota bene here is that in these two models, model LE and G, we always have W2 of n equals W3 of n, because as I explained, we do either, at every step, we do either +1 to this edge or +1 to these two edges. So the weights of these two edges is always equal. And this means that the effective conductances of this between n and F2 is now equal. So I just apply this formula, but I plug W3 of n equals W2 of n, and what I get is W2 of n divided by 2. So what I get in total is that this is W1 of n divided by W2 of 2 of n half plus W1 of n half. Plus W1 of n. Right. So again, if you like Pólya urns, what you see here again is just, you can interpret this as a number of purple balls and a number of green balls in an urn. But the difference here is that the weights of the balls are different, which I shouldn't call them weights, but you have to imagine. So in my head, I like imagining that the purple balls are much bigger now than the green balls, and that when I pick a ball at random in my urn, a purple ball is twice likely to be drawn than a green ball, right? Because they are bigger, so I'm more likely to pick them. So, and in that case, the fact that these purple balls are more likely to be picked makes such a big difference that in fact the proportion of purple balls, so in that case, again, it's not very complicated to prove, but in that case, oops, it's been proved already in the Pólya urn literature that the weight of the purple balls goes almost surely, when n goes to infinity, to 1, which is great because it means that this weight here goes to 1, so almost all the aunts go there. And we know that this means that the weight of this edge goes to 0, right? Because an aunt is going to reinforce either this edge or that edge, but not both. And since W3 is equal to W2, then the weight of this edge also goes to 0. So we are done. And I really like this example because if you know reinforcement learning, you could have been wondering. So in reinforcement learning, the idea is that you do a trial, and if the trial is successful, you give a reward to the strategy you've used. And the reward here is our +1, right? Is reinforcing edges. And it's really weird because we give a reward anyway, even if the trial is successful. We don't ask, you know, is the trial successful or not? We just give +1 to our, you know, to our chosen trajectory. But here you can see that when I pick when I give a reward to this edge, in my Pólya analogy, I'm adding a big purple ball, so a big reward. Whereas when I picked the longer path, then I'm still giving a reward to the longer path, but it's a small green ball. So it's a smaller reward. So somehow we always give a reward, but the reward is a bit bigger when we've chosen a shorter path. Great. So in model T, what happens? In model T, on this simple graph, what happens exactly? So the main difference is that in model T, we don't have this. We don't have this here. We don't have equality. But in model T, we still have W2 of n is larger than W3 of n, because we cannot do +1 to this edge without doing +1 to that edge, right? Because of the aunt can't cross this edge without crossing this edge. So, and this inequality means that here I don't have equality here, but I have inequality. So I have that this is less or equal to that, right? And this means that I have also an inequality here, which is larger or equal. And so somehow here we're doing a coupling, and we're basically saying that the renormalized weight of this edge is even larger than the proportion of purple balls in my urn. So it has to convert, the lim inf has to be bigger than 1, and we know that it can't be larger than 1. Okay? So it still converges to 1. So in model T, we still have this convergence to 1, which implies that the weight of edge number 3 goes to 0, but which doesn't imply that the weight of this edge also goes to 0. So in model T, we need to prove that the weight of the second edge divided by n goes to 0 when n goes to infinity, if we want to find shortest path, right? Okay, so let's have a look again. So what's the probability? So again, it always starts with the same calculation. What's the probability that I reinforce edge number 2 at time n, knowing all the weights up to time n? And this time again, we do the conductances method. This is the probability on that graph that I reach this node before reaching that node starting from n. So again, with the same formula as before, this is equal to Wn divided by W1 of n plus W2 of n. Great. I'm just going to introduce a notation quickly. I'm going to add hats to say that Wi hat of n is just a renormalized version. And you can see here, I can just divide the top and the bottom of my fraction by n, and this just adds hats everywhere. I'm doing this because now what's quite interesting is that because of this, we know that the term, this thing here is approximately 1, which means that here it's approximately W2 hat of n divided by 1 plus W2 hat of n. And this is where stochastic approximation comes into play. So if you know stochastic approximation, you see one here now. So from here, it's very easy to prove that if you can write W2 n plus 1 hat in terms of W2 n of hat. So you have a recursion equation, which tells you that this is W2 hat of n plus 1 over n plus 2 times, it's n plus 2 because I want to put n plus 1 here, sorry, times a function of W hat 2 of n plus delta mn plus 1. So this is really straightforward from here. And in fact, the function where f of x is just this function minus the identity. So it's x over 1 plus x minus x, which you can calculate is in fact equal to minus x squared divided 1 by 1 plus x. And this is when we're going to use the ODE method. So when you have a stochastic approximation, intuitively, what should happen if f is nice, so if f is Lipschitz and if your martingale increment is bounded in particular, but also in other more complicated cases, then you have that your sequence of random variables follows the flow of the differential equation y dot equals f of y. And here in particular, you can notice that f is negative, right? So f is negative on 0, 1, right? So x, here I'm just looking at this function on 0, 1 because y hat 2 lives on 0, 1. And this means that this flow here, so you always have a negative derivative, and therefore you're always decreasing, but you know that you live on 0, 1. So somehow, if you follow the flow of this equation, then you have to go to 0. Therefore, W hat 2 of n goes to 0, which is exactly what we wanted to prove, because W hat 2 is just W2 divided by n. And so this is how you can see, I'm running out of time, but this is how hopefully on these 2 little examples, we can see. So first we can see that model T is more complicated than model, the other 2 models, right? The geodesic and the loop erased one, because it's a bit more complicated. And we can see why it's going to be harder to find shortest path, right? Because in model T, even if eventually I go through that edge, which is good, I can still reinforce that edge number 2. And so this is what is going to make model T not be so good to find shortest path. And also for the mathematical analysis, we can see that it's harder. There are more things to prove, right? It's not as straightforward. And so I think that's all I wanted to say, really. Maybe I can finish on some open problems. So as I hope I have convinced you that this is a very rich mathematical model, and that when we change a tiny bit the reinforcement rule, right? I've shown you 3 different reinforcement rules, and these can induce drastic different behaviors for whether or not we find shortest path. And of course, the first open problems we can think of is whether we can prove some of the conjectures I gave you in this talk. Of course, in the book as well, to see things in a wider context, in the book I cited at the beginning, the on-colony optimization book, there are other reinforcement learning algorithms that are described, and the question is whether we can also introduce some probabilistic models for these problems, and whether we can also analyze them to show whether or not they actually converge to the optimal solution. But this will be for later. Thanks a lot for listening to me. I hope, and I'm happy to answer all questions you have.
Let's thank our speaker. Thank you very much, Cécile. And many thanks for giving the talk on your not black but whiteboard.
Whiteboard, yeah.
Yes, I think it's, at least for me, it's much easier to take home something when
Great.
Talk is given like this, not on slides. Okay.
I'm glad.
So, yep. Please, questions, comments. Just ask.
I have a question. Thank you very much. Really interesting talk. And especially because last 2 months I was involved in a lot of ants problems. So my son is doing science in high school, and he catch ants, and he just measured random simulations and interactions between ants. So 2 months we did all projects with real ants. Now I am really excited about this talk. And mathematical question is the following. So you have this limiting distribution. Yeah, so limiting weights, which of course corresponds to some limiting probabilities. So if you have these limit probabilities, then you can compute average time to reach food. Average expected time or expected time to reach food from the source. So you say if you pass each age with time 1, so you can compute this average time and you can compare with the short path. So then probably you can argue that in some cases or for some graphs, and it's not very stupid. So the average time is very close to optimal. So, and maybe you can look at it, it's like you somehow try to interpret this as not Markov, but another type of chain. So you would like to find asymptotic properties. So it could be a lot of interesting problems related to this limiting distribution and how to write this using different matrices. Have you tried to do something like this?
Yes, no, not at all. But it's I find your question interesting because something I mean it gives me the option to say something is that in fact even if we say we find shortest paths, so maybe let me go back to when this example wasn't so good. Let me go back to a graph. What graph do I know? I'm going to give you a new example. So let's say we have a graph like this. Okay, and we say, so the nest is at the top, the food is at the bottom, and we say, okay, so we say that the limiting weights are going to be 1, 1, and 0, 0, 0, at least in the loop erased and the geodesic model. But in fact, it still means that the ants can still waste a lot of time, in fact, doing back and forth here, because we don't look at non-backtracking. So the ants are allowed to backtrack. So in fact, but I still think, as you say, we probably still have some optimality in terms of time to reach to hit the food, but it's not. Yeah, it's not optimal in the sense that they're not all going to reach the food in time 2 here. For that, we would have to have some kind of backtracking. But as you say, the ants never backtrack in real life. So this is maybe a flaw in our model, that we allow the ants to backtrack.
Yeah, but these averages can maybe help to understand some aspects of your model maybe a little bit better, yeah.
Yeah, that's completely true. So we haven't quite tried that, is my real answer to your question, aside from digressing. But yeah.
Okay. Yep. Any further questions, please?
Yeah, have you thought about having other kinds of reinforcement other than like linear reinforcement? Does it make it harder or easier? Or,
So the answer is no. So at first we thought, in fact, we were a bit surprised, because at first we thought we would need to do, so our aim, you have to understand that our aim when we started looking at this project was we want to find algorithms that find shortest paths, right? And at first we thought, okay, we probably need to do superlinear reinforcement. And in fact, this is a mistake. So we are now convinced, and you can convince yourself on this example, in fact, that superlinear reinforcement is not going to find the shortest path, or at least not always. With positive probability, the ants are just going to go through that path. And it's because when you have superlinear reinforcement, the first few ants are going to have too much of an impact. So if the first few ants go through that way by bad luck, then it's probable, with positive probability, all the ants eventually are going to go there. And it's something that often happens in superlinear reinforcement. And in fact, in these papers that I cited here, this is basically what happens intuitively, is that even though it's self-reinforcement, but it's super linear. The ant, you know, starts going completely at random, you know, like a normal simple random walk, but eventually it starts going back to a few edges it's already visited, and then it just concentrates on this random cycle somewhere. But the random cycle is random and it's not really optimizing anything. So super linear reinforcement would convert somehow, but not always to the shortest path. And we believe that sublinear reinforcement would just find nothing. So all the edges would have a positive renormalized weight at the limit. So it would just find nothing.
Yeah,
which again is a bit.
That's what happens with the Pólya urns, right? You just get like a uniform kind of thing. Right?
Exactly. That's what happens with the Pólya urn. And one thing we were wondering though, so when I talk about superlinear and sublinear, is that the ant chooses to cross an edge with probability proportional to the weight to some power, alpha, which is either more than 1, equal to 1, or less than 1 in the 3 different cases. But you could imagine something a bit more subtle. So you could imagine maybe you do some sublinear reinforcement, but you choose another concave function, which is less concave, not as bad as, you know, a power less than 1. And I think we were thinking it would be interesting to see when it breaks down. So it could be that for some functions that are close enough to linear, you still find shortest path, but when you become too close to n to x to the alpha, then you don't find shortest path anymore. And I think it would be very interesting to see if there is a transition. Maybe it would be a bit hard, but it would be very interesting to look at.
Yeah, I'm actually not sure what happens with like just Pólya urns in that intermediate regime. So
I'm not sure either, in fact. Yeah, that's a good one. Maybe we should start with Pólya urns.
Any further questions?
I have a simple question to ask. So in your example B, you gave this linear graph between n and different, so F1 and F2 in example B. So
yeah.
In what is it always possible to get such a linear graph, or in what possible graphs you can give this relation and get a conductances for the edges?
Okay, so well, the linear graph is very specific to this example, I would say. Okay. Maybe in trees always. So in trees always, because in trees you may have some little branch. So if you have a tree-like graph, I think probably you can always go back to this. You might have a tree going there, but it doesn't really matter when you have dead ends. So it wouldn't, I mean, so basically you can ignore all the little trees that hang out that don't contain F2, N, or F1. So in tree-like graph, you can get this. But otherwise you can, so that's also the advantage of looking at series parallel graphs, because series parallel graphs are really the graphs for which calculating effective conductances is easy, because you just apply the formulas, you know, so two graphs in parallels, you just add the effective conductances to get the effective conductance of the big thing, and 2 graphs in series, you just do this formula here with the inverse of the conductances. So somehow series parallel graph is really ideal to use this electric conductances method. But there are also, so if you look at the book of Lola and Limich, if you're not in the series parallel case, there are other formulas that can help. So in particular, there is a transformation triangle to star, so which basically allows you to calculate effective conductances when you're in a case like when you have a triangle. You can transform it into a star and you have formulas that give you what are the weights of these 3 edges, so that as a function of the weight of these 3 edges, so that the effective conductances between the 3 nodes are kept unchanged. So there are lots of formulas for that, but otherwise to have really the linear thing, I would say tree-like is probably the safe thing.
But to get this urn model, you don't need that linear graph, right? If you know the conductances, you can get the corresponding urn model.
No, so it can become very complicated because so the
I'm not
because
sure if my question makes sense.
No, it does make sense. But the thing also intuitively, if you want, for me, I can almost say that every graph is somehow an urn, but it's more lots of urns that interact with each other in a very complicated way. And the reason is that if you have two graphs in parallel, say you can say, well, I'm going to go through the left graph with probability proportional to its conductance and the right graph with probability proportional to its conductance, and I could see that as a big urn, right, where I say the urns that go to the left are my purple ball and the urns that go to the right are my green balls. But unfortunately, the problem is that then when you pick a purple ball, so when you went through the graph on the right, then you don't just do a +1, you do a plus something complicated.
Yeah.
And that's a bit what becomes complicated when you look at bigger graphs. Here, I was always just doing +1 to the left, but if I had here a very complicated graph, I do, +1 to a certain number of edges, and the question is, how does it impact the conductance of the graph? But this is more or less how we prove the stuff for series parallel graph. We just evaluate what's the change, given our induction assumption, we kind of know what's the change to the conductance when an aunt reinforces the graph to the left. And even though it's not a +1, it's plus something we can estimate. So yeah, thanks a lot for this question. I mean, yeah, it's really the heart of the proofs.
Okay.
And why is it that you say, even though in the T model, this W2 hat n goes to 0, so the weight of the edge 2 is going to 0.
Yeah.
So eventually you find the shortest path, isn't it?
Yeah, so in this graph, yeah, so it's because this graph is one of these. So if you remember, I had I said in the theorems, where is my theorem? Here I said if the graph is tree-like and the distance between n and f is 1, and this is exactly the case in that example. So the graph is tree-like, and so I find the shortest path. But in more complicated graph, I might not. But in this graph, yes, it's normal.
Okay. Yeah. Thank you. Very nice stuff. Thank you.
Thanks.
I have one question more.
Okay.
Yeah. So say you look at this asymptotic distribution of weights. Is any way from these distributions to tell, at least in some cases, what kind of reinforcement was used? So, for example, limiting distribution, and just maybe not in all cases. In all cases, I understand it's very difficult, but that at least you see that these classes, they are not identical.
Yeah, so well, so there are obvious cases, right? So for example, the difference between T and the other two model is clear because in some cases you find shortest path, in some cases you don't. So this is very clear that then, you can just look whether you find shortest path or not, and you can say whether you were in model T or not. Mm-hmm. But this is, so for example, in the Lozange case, so yeah, let me go back to the Lozange case in this case. So here we're able to prove that so this theorem basically tells us that in the geodesic case, you're going to have weight zero here on that edge, and you're going to have weight some random variable x on the left and some random variable 1 minus x on the right. And the only thing we know is that x doesn't have any atom at 0 or 1. But in fact, we tried to understand what's the distribution of x, which would be your question, because we believe the same is true in LE. So in the loop erase model, we believe we also have some x random variable and some 1 minus x. And your question is basically, do you know the distribution of this random variable x in the two models? And therefore, can you make the difference? Can you see the difference on the limiting graph, right? On the limiting weights? And the answer is, we think it's very hard to describe the distribution of x, the random variable x. We tried a bit. For example, we wanted to prove that it has a density on 0, 1, and we couldn't, right? And in fact, already proving that it has no atom at 0 or 1 was quite hard. So my answer is we can't do what you're asking for yet, but it would be great, of course, to do it.
Okay, thank you.
So Andrew, why don't you run simulation on your ends from your sample project and see how it works?
Yeah, ends not running this reinforcement.
It's too cold. Okay.
Yeah, they ran randomly. Okay.
Right. At least you can collect statistics next summer and perhaps provide it to Cécile. So
that would be nice.
Okay.
Okay. Perhaps one more question. No questions. All right, then, Cécile, thank you very much again for giving this talk. It's a great pleasure.
Having me.
Thanks for coming to Australia.
You're welcome. Thanks a lot.
Okay.